Welcome back, calculus class. We're going to look at section 4.4 today. Concavity, points of inflection, and the second derivative test, which we're really just going to focus on concavity and points of inflection. So the objective, let's see if we can find out determine intervals of concavity, whatever that is, locate points of inflection, whatever those are, and use the second derivative test, which we're not going to do in this video. So determine concavity, whatever that means, and points of inflection. So here's a graph right here. Looking at the graph, what's one thing I can say about the function? There's many things we can say, but one thing I want to say about the actual function is it's increasing. So what can we say about the derivative of the function? So the fact that the function is increasing, what does that mean about the derivative? If the function's increasing, that means the derivative or the slope is positive. Algebraically, that means that the derivative to be positive, the derivative is greater than 0 everywhere. So all these, no matter what x value you're at, if you find the slope and plug in a number, you'll get a positive number. But one thing that's going on here is the slope here is a little bit different than how the slope's behaving here. So here from, let's say, -1 to 0, the function's increasing, but the slope is getting less and less and less steep. So the slope is getting less and less steep means the slope's getting smaller and smaller and smaller. So even though the derivative is positive, it's still decreasing on that interval. So although the slope is positive, so the function is increasing, but the slope, it's increasing at a decreasing rate there. So what that means is if the derivative is decreasing, then the slope of the slope, which we call the second derivative, is negative. From 0 to 1, the function's positive, and so the derivative is going to be positive, and it's increasing, but it's increasing more and more and more and more and more and more and more. The rate of change is getting even faster, so it's increasing a little bit here, but it's increasing a lot of it over here, so the slope's increasing. So the derivative is increasing. So if I took the slope of the slope, which is the second derivative, that's going to be greater than 0, positive. So over here, the second derivative would be negative, less than 0. Okay? So this idea of concavity. So take a minute to write it down, but let f of x be a differentiable function on a given interval. We say it's concave up on the interval if f prime is increasing. So visually, what concave up means is it's opening upward. So something like this would be concave up, and something like this would be concave up. Okay. In both situations, the slope is increasing. So it's not going to take much to convince you that the slope's increasing here. But what's going on here is that the slope, the function's increasing, but the rate of change is getting steeper and steeper and steeper. So the slope is going to be increasing. Here you might say, well, Mr. Flora, the function's decreasing. I agree with you that the function is decreasing, but the slope is actually increasing because the slope here is like a very negative number. Maybe it's like -10/1. That's a very steep negative slope. And here the slope is like 1. And now the slope is getting like closer and closer to like a half or 0. So although the function is decreasing, the slope looks like it's going flatter and flatter and flatter. So the slope is increasing. So we're going to call that concave up. To be concave down, the slope is decreasing. So something like this. Ooh. Or like this. Again, I understand that. So this one will be easy to convince you that the slope is going from like, almost 0 to like -1 to like -5. So the slope of 0 to -1 to -5 over 1. So it's getting steeper and steeper and steeper. So it's getting more and more negative because it's decreasing. Now here it might be a little bit harder to convince you that the slope is decreasing. I understand the function is increasing, but the slope's increasing super fast in the beginning. That slope looks like, I don't know, maybe like 10 over 1, but then it's starting to flatten out. Now the slope's like 1 over 1, and then it's getting closer to like maybe like 1 over 3 or something like that. So the slope is getting smaller and smaller and smaller. So that's what we call concave down. So opens down. All right. So how can you determine if the derivative is increasing or decreasing? Because that's what we call concavity, if the derivative is increasing or decreasing. We need the second derivative. So if I want to find out if this function is increasing or decreasing, we take its derivative. So I got to take this thing's derivative, which we call the second derivative. So find the second derivative. If I want to find the rate of change of a function, I find its derivative. If the rate of change of the function I'm looking for is a derivative, I need to find that's derivative. So that's why we need the second derivative. So I'm just going to sketch a curve for you. And just draw where you think it's concave up and concave down. And when it's concave up, it's opening up. So right about here. And then at some point it switches and it's opening down. And then it's switching again and it's opening up. And then it's switching again and it's opening down. And then later at the end it starts opening up again. So this is concave up. And this is concave down. Okay. So visually, that's what it is. And by the way, these points where the concavity switches are called inflection points. Okay. All right. So pause the video, take a minute to copy this down. So a question is, where is the function concave up and concave down? And visually speaking, it's pretty easy to find. But if I was just giving you a function rule without a graph, first we want to find out where the concavity switches. So I want to find where these possible points of inflection are. And that's where the second derivative is either 0 or does not exist. So we are using the first derivative test on the first derivative is what's really happening here. So the skills are the same as last lesson. Once you find out where the second derivative is 0, you use these values to define the intervals. So where the second derivative is 0, we have a possible point of inflection. Everywhere else, the second derivative is either going to be positive or negative, which would tell us it's either concave up or concave down. Find the value of the second derivative on each interval using a test point. If we get a positive number, that means if the second derivative is positive, that means the first derivative is increasing, which means the slope is increasing, which means it's concave up. If the second derivative is less than 0, that means it's negative. If the second derivative is negative, that means the first derivative is decreasing. If the slope is decreasing, we call that concave down. Also pause the video to copy down the points of inflection. F of x is a point of inflection at some value c if all the following are true. So if at this point the derivative is either 0 or does not exist, the second derivative has a sign change, and the value of c in your original function is defined. So this is one that we often forget, but you have to, not only is it where the second derivative is 0 or doesn't exist, but it's also going to be defined in the first derivative. When we see an example, you'll see how this all works out. But again, when we have that sign change, that's when we switch from concave up to concave down. So if I switch from concave up to concave down, boom, I have an inflection point. If I switch from concave down to concave up, boom, I have an inflection point. right? If we don't have a sign change, then I'm concave down, and then I'm still concave down, no sign change. I'm concave up, and I'm still concave up, no sign change. So when we have a sign change, this is what a point of inflection looks like. If there's no sign change, then this is probably what's happening. Okay. So determine where the function's concave up and concave down, and let's find some points of inflection, which I am going to refer to as points of inflection as POIs. Okay. So to find out where the function is increasing or decreasing, concave up or concave down, we need to find out what the second derivative is. So first, let's find the first derivative. It's going to be 3x squared minus 3. The second derivative is going to be 6x. So I want to find out where this is either 0 or does not exist. And 6x is always going to exist, so we just want to find out where it's 0. So the second derivative equals 0 when 6x equals 0. So that's when x equals 0. If you want to find out where the second derivative does not exist, it's not happening. It's going to exist everywhere. Okay. Is 0 defined in my first derivative? Can I plug 0 into this function? And yes, if I plug 0 in, I just get negative 3, which is fine. So it's defined in the derivative 0. So we have a possible inflection point. And we've also we found out where the derivative 0 does not exist. And we're going to use that to define our intervals and find out where it's concave up and concave down. So now if I make a sign chart for my derivative here, excuse me, second derivative. All right, second derivative 0 at 0. If I plug a number less than 0, let's see if it's positive or negative. So if I use negative 1, if I plug negative 1 into this, I get 6 times negative 1, which is negative 6. I don't care that it's negative 6, I just care that it's negative. So it's negative here. If I plug a number bigger than 0 in, like 1, I get 6 times 1, which is 6, which I really don't care what number is, I just care that it's positive. So what this means now is that my function is concave down from negative infinity to 0. So let's talk about my original function here. From negative infinity to 0, it's concave up because the second derivative is positive from 0 to infinity. And we do have a sign change, so we have an inflection point. And we have a point of inflection at 0, comma. I got to plug 0 into my original function here. If I plug 0 in here, I get 0 cubed minus 3 times 0, which is 0. Okay, and that's it. So we're just kind of using the first derivative test on the first derivative. So we're using the second derivative to find out information about our function, and the second derivative tells us the concavity, the rate of change of the rate of change. Okay. By the way, this is a cubic. It's probably going to look something like this. At 0, 0 is where that point of inflection happens. Okay. And it's concave down and concave up. All right, last example. Determine where it's concave up and concave down and any points of inflection. So we're going to need the second derivative. So let's start with the first derivative. So there's two ways we can handle this, and I'm just going to do it the way that I think the majority of us would do it. But I'll show you that there's another way that could have gotten us the same answer. But anyways, so this is a quotient, so use a quotient rule. So low d high, the derivative of 6 is just 0, minus high d low, the derivative of the bottom is 2x, over low or low squared. So 0 times this is just going to be 0. So I'm going to get negative 12x over x squared plus 3 squared. Alternatively, I'm going to erase this, but I'm going to show you, you could have rewritten this as 6 times x squared plus 3 to the negative 1, right? Cross the line, change the sign. And then if I wanted the derivative of that, I would just use the chain rule. So negative 1 times 6 is negative 6. Leave this alone, subtract 1 from negative 1, you get negative 2. times the derivative of the inside. The derivative of the inside is just 2x. Negative 6 times 2x is negative 12x. And this goes to the denominator and becomes x squared plus 3 to the positive 2. Again, cross the line, change the sign. We get the same thing either way. But, do it however you want to do it. I just think most people would use the quotient rule here and wouldn't think to rewrite it and use the chain rule. So now I need to find the second derivative. So let's find the derivative of the derivative. So I'm not going to use that same trick because then I'd be using the product rule and it's just not worth it because there's an x up here. Here the numerator just had a constant, which is why I did it. So I'm going to do the same thing. Low d high minus high d low. The derivative on the bottom is going to be a chain rule. It's going to be 2 times x squared plus 3 to the first, which I'm not going to write, times the derivative of the inside, which is times 2x. All over that. So let's do some cleaning up. So let's see here. They both have an x squared plus 3 that I could factor out. And they actually both have a negative 12x, a negative 12 that I can factor out. So I'm going to factor out a negative 12 times x squared plus 3. That's super simplification stuff. There's still one x squared plus 3 factor here because to the second power. I'm factoring out this negative 12, so there's nothing else here. You don't need the parentheses, but I'm just going to put them in there. Now, this negative 12 is gone, but I still have a minus 2x times 2x. So minus 2x times 2x is minus 4x squared. And this whole highlighted part and this highlighted part have been taken out. So that's it. Over x squared plus 3 squared. Now, this x squared plus 3 is factored out, so that's going to take out one of those factors, which is nice. So then I'm going to be left with negative 12, and then x squared minus 4x squared is minus 3x squared. So I'm going to have minus 3x squared plus 3 all over x squared plus 3. I guess I didn't need to factor out that negative 12 because I'm just going to multiply it in now. So just distribute that into there, and then I'm going to get a positive 36x squared minus 36 over x squared plus 3. So that's my second derivative. Now, where is this thing 0 undefined? So the second derivative equals 0 when the numerator equals 0. So that's when 36x squared minus 36 equals 0. Add 36 to both sides. Divide both sides by 36. So x is going to equal plus or minus 1. Real quick, can I plug plus or minus 1 into my original function? Absolutely. Whether I plug 1 or negative 1, I won't get a 0 in the denominator, so we're good. So let's find out where the second derivative does not exist. That's where the bottom equals 0, which is impossible. That would mean x squared would have to equal negative 3, and there's no solution to that. So that's never going to happen. So these are what I'm going to use to define my interval. So we have negative 1, and 1 is where the second derivative is 0. Let's see what's happening outside of those intervals. So if I look at negative 2, a number between negative 1 and 1 like 0 we'll look at, and a number after 1 like positive 2. Again, I just want to know if my second derivative is going to be positive or negative. So I plug in negative 2, I get about 0.315, which is a positive number. So it's going to be positive there. Again, you can plug numbers in here. The denominator is always going to be positive because it's something squared plus 3. So I know, the denominator is always going to be positive. And the numerator, I'm going to square negative 2, which is going to become a positive 4. And then 4 times 36 is going to be bigger than 36, so that's going to be positive. So, boom, positive. If I plug in 0, I'm just going to get negative 36 over 3, which is negative 12. It's not negative 12, but it's a negative number. Oh, I made a mistake. When I did the quotient rule, this should be squared, which would make this a 4. So when I cross out this factor, that becomes a 3. Okay, that makes sense. All right, not a big deal. It hasn't changed anything yet. So if I plug in 0, I get 36 over 27 because it's 3 cubed. Either way, like I said, we're going to get a negative number. What did I get? About negative 1.33. But it's negative. Ooh. So the function's going to be concave down there. And if I plug in positive 2 into this thing, again, the numerator 2 squared times 36 is going to be bigger than 36. So that's going to be a positive number up top. The bottom, 2 squared plus 3 is going to be positive. You keep a positive number, it's still going to be positive. So we're going to get a positive number. It ends up being about 0.315 again. So this tells me that my function's concave up everywhere except between negative 1 and 1. So f is concave up, negative infinity to negative 1, union 1 to infinity. And it's concave down from negative 1 to 1. And we have points of inflection at, if we only have a sign change. If we have a sign change here, it's going from plus to minus and minus to plus. So at negative 1 and at positive 1. And I got to plug those numbers into my original function. So if I plug 1 into here, 1 squared is 1, 1 plus 3 is 4, 6 over 4 is 3 halves, that's 1.5. If I plug negative 1, I'm going to get the same thing. Okay. All right, that's it for the video. There's more that we can talk about, but for now, that's fine. If you like this video and you want to see more like it, please let me know in the comments. I'd love to hear from you. And I want to give a big shout out to Raid Shadow Legend for sponsoring this video. Have a nice day.